Okay, geometry students, in this video, we will be studying three properties of tangents, okay? Three properties. Now, these three properties will be given to us in the forms of theorems. We will also look at what it means for a circle to be inscribed and circumscribed, okay? Your heading for today is Properties of Tangents, Lesson 10.2, and be sure to include today's date in your notes. Okay, Properties of Tangents, Lesson 10.2, and be sure to include the date today for your notes. Alright, now, like usual, we don't have a lot of time to spare in this class, so let's jump into this right away, okay? Theorem 10.1 that we're going to look at today. Theorem 10.1. Please copy this in your notes. You're responsible for this, and we're going to talk about it in just a second. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Okay? Please copy that in your notes. If a line is tangent to a circle, then that line is perpendicular to the radius drawn to the point of tangency. Alright? It's a little confusing. Probably a lot of you understand what it's saying. Some of you might not. So I'm going to give you a picture here in just a minute and explain this to you very well, okay? Please copy this down. Excuse me. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Alright, here we go. Please take some really good notes, students, okay? Go ahead and draw a circle in your notes the best that you can. And go ahead and draw a radius. And then draw a line that's perpendicular. Just like this. Or not perpendicular, I'm sorry. Draw a line that's tangent to the circle. And let's label that point right there A. And we'll call this circle B, okay? Let's call this line right here line L, okay? If I can get my pen to work here. So there we go. Alright. So please copy this in your notes and then come over here and put this. If line L is tangent to circle B at point A, okay? If line L is tangent to circle B at point A, then AB is perpendicular to line L. Okay, let that sink in. Copy this down. Then I'm going to talk about it a little more, okay? If line L is tangent to circle B at point A, then AB is perpendicular to line L. So students, listen to me. Anytime you have a tangent line and a radius drawn to that point of tangency, then these two lines will be perpendicular. So if we move the circle out of the way, what we're saying is there's a right angle right here. This line here is the radius. This line here is the tangent line. And this is the point of tangency right here. Okay? So that's what this theorem is saying. Alright, now, by the way, I'm not going to make you prove it. We're not going to talk a lot about that. But I will say this. How do we know for sure they're perpendicular? I mean, you've been told all year by me to not go by the naked eye and just look at stuff, but to go by facts and what you can prove, correct? So it's the same thing here. They look perpendicular, and it's kind of common sense, but how do we know for sure? Well, I'll show you how we know for sure, guys. Here's the center of a circle. Here's the radius being drawn, correct? Well, we know that if I draw any other lines to line L, the line would first have to hit the circle and then go to the line. Hit the circle and then go to the line. So any line that I draw other than BA will first have to hit the circle and then continue on to the line. The only line that I can draw that. Alright, one more time, we're moving on. If you have a tangent line and a radius is drawn to the point of tangency, these two lines will be perpendicular. They will form a right angle. Now, as we've learned in the past, not all converses are true when it comes to theorems, but in this case, the converse is true. So theorem 10.2 is just the converse, okay? So here it is. In a plane, if a line is perpendicular to the radius of a circle at its endpoint on the circle, then the line is tangent. Okay, that's pretty confusing. Go ahead and copy it down. You're responsible for it, and I'll put this. I'll explain this a little better in just a minute. Okay, copy this down, please. In a plane, if a line is perpendicular to a radius of a circle at its endpoint on the circle, then the line is tangent to the circle. And I'll explain that in just a second. Okay, let's go ahead and draw a circle, students. In your notes, go ahead and draw a circle if you would, please. And I'm going to draw a line as tangent to the circle down here. And here we go, students. Please take some really good notes. Now, we're going to call this line M, and we'll call this point C and point D, okay? Now, now watch this carefully, students, please. What it's saying is this. If a line is perpendicular, so if M is if line M is perpendicular to a radius, and of course the radius is DC. If line M is perpendicular to radius DC at its endpoint, which is right here. So if line M is perpendicular to radius DC, then I can state line M is tangent to circle D. So they're inverses, students, or converses. Listen, in theorem 10.1 it said if a line is tangent, then it's perpendicular to the radius. Down here they're saying if a line is perpendicular to the radius, then it's tangent to the circle. It's just the converse, okay? So if I have a line that is perpendicular to the radius and it's perpendicular at the end point right here, then line M is going to be a tangent to the circle, okay? So, pretty much just what we looked at before in theorem 10.1, now it's just reversed in theorem 10.2, and you actually could have written both these theorems as one if you use the words if and only if. Like you could say something like a line is tangent to a circle if and only if it is perpendicular to the radius, and that would cover both theorems, okay? So 10.1, if a line is tangent to a circle, then it will be perpendicular to the radius at the point of tangency. And if a line is perpendicular to a radius at the point of tangency, then the line is tangent to the circle, okay? So there's these two theorems here. Let's go ahead and continue on. Now, notice these two theorems are converses of each other, and I've already talked about that. Let's take a look at a problem for a minute, okay? So copy this problem down in your notes, please. Let's take a look at this. Copy this in your notes, please. Now, here's my question to you. How do I know for sure that DF right here is tangent to circle E? How do I know for sure that DF is tangent to circle E? So copy this down. I'm going to wait just another minute. Students, go ahead and copy the circle, these numbers, the triangle, and then write the question. How do we know that DF is tangent to circle E? I know it looks like it, but how do we know that it is? Okay, here we go. Well, remember the two theorems we just looked at, okay? If a line is what? Perpendicular to the radius, then I know the line is tangent. So if I'm asking you, is this line right here tangent? The best way to prove or show that it's tangent is to show that I have a right angle right here. If I have a right angle right here, then I know that DF is perpendicular to the radius. Thus, that makes DF a tangent. That's what theorem 10.2 says. If a line is perpendicular to the radius, then the line is tangent to the circle. So, how can I prove that I have a right angle here? Well, I know how to do that. Remember Pythagorean's theorem. Let's see if I have a Pythagorean triple here. Take your two shortest sides, 11 and 60, square them, and set them equal to the longest side squared. Okay, let me grab my calculator real quick here. 11 squared plus 60 squared is going to give you 3,721. 61 squared also gives you 3,721. So we do have a Pythagorean triple. Thus that means I have a right triangle. Thus that means I have a right angle. So if I have a right angle, DF is tangent to, DF is perpendicular to DE, which means DF has to be tangent. Okay, so there we go. How do we know for sure? By proving that we have a Pythagorean triple, thus proving that we have a right triangle. Alright, let's take a look at another problem. You were standing 17 feet from the water, a large water tank. So here's the large water tank. You've seen these in cities and stuff like that. Here it is, really big, and you're standing right over here, feeling kind of small, okay? So there we go. Now, you're 17 feet from the large water tank. Let me stop, guys. I never really gave you time to copy this down. I apologize. Go ahead and copy this problem down, and then do the best you can to draw this, okay? You're standing 17 feet from a large water tank. The distance to a point of tangent C is 53 feet. What is the radius of the tank? Copy this down, please. You are standing 17 feet from a large water tank. The distance to a point of tangency on the tank is 53 feet. What is the radius of the tank? Now, we're going to pretend that we can see through this tank, okay? So you're standing here. Now I'm going to draw a line to a point of tangency. It's going to be really hard to do. Right here is going to hit right here, alright? So this line from here to the point of tangency is 53 feet. Okay? Now, let's go ahead and draw a radius here. And then a radius here. Alright? Now, let's get this labeled correctly, okay? From here to here is 17 feet. From here to here, I have no idea. I'm going to call that X. We'll call my radius X. Also, students, though, this would be X2 because it's a radius, okay? Now, remember, I know it doesn't look like it, and I know this looks really, not drawn to scale. But remember, that's why we go by the theorems and what we know to be true, not by what we necessarily see. So, remember students, wherever a line is tangent to a circle, there's a right angle right there. So there's the right angle of my triangle, okay? So I really have a right angle, like this, right here. Now this length here is 53 degrees, okay? Now this length here is X. And then of course here, from here to here is my X. y'all see it a little better, okay? Now, so let's review very quickly, okay? Standing here 17 feet away, 53 feet away is a point of tangency, so I draw a line here. This is where the right angle has to be, because this is where the point, this is where the line that is tangent to the circle is intersecting the circle right here. And we've learned that a line that is tangent to a circle is always perpendicular to the radius, okay? So even though it doesn't look like it, I'm not a very good artist, there's your right angle. So how can I find the radius, guys? Well, Pythagorean Theorem, guys. Look, what's one of your legs? 53, okay? What's another one of your legs? X right here. Now, what is your hypotenuse? Well, it's x plus 17. X plus 17 squared. So here's one of your legs, 53, square it. Here's one of your legs, x, square it. Here's your hypotenuse, x from here to here, plus 17 from here to here. So there's your whole hypotenuse squared. Now if you square 53, you're going to get 289. Alright? Plus x squared. And x, that's not correct, sorry. If you square 53, you're going to get 2,809. 2,809 plus x squared. Now students, whether you've had just Algebra 1 or Algebra 2, you should remember how to do this. You have x plus 17 quantity squared, which means x plus 17 squared, okay? So you take the x, you multiply it through, take the 17, you multiply it through. If you do all of that correctly, x times x is x squared, x times 17 is 17x, 17 times x is 17x, and 17 times 17 would be 289. Let me go over that again, okay? You take your x and you multiply it through. X times x, x squared. X times 17, 17x. Then, you take your 17 and multiply it through. 17 times x is 17x. 17 times 17 is 289. Okay? Now, if we combine our like terms, we have an x term here and an x term here. So really what I have is x squared plus 34x plus 289. But I notice something. On one side I have an x squared, and on the other side I have an x squared. They're identical, so I can really cross them off, or cross them out, or cancel them out. Or in other words, if you don't like that, bring the x squared over and make it a negative x squared, and it cancels them out. Either way, your x squareds are gone, okay? So I do notice I have a positive x squared on both sides of the equation. So I go ahead and I cancel those out. Alright, let's get rid of those. Now after that happens, I'm really left with a pretty simple linear equation. Okay? I really am. All I have to do is get my constant terms on one side and my x terms on the other. So take this 289, bring it over, make it a negative 289. And you're left with 1800. And that's not correct. Sorry about that. And I believe right up here, guys, let's see. This is 28. Man, guys, I'm sorry. This should be 2053 squared is not 2089. It's 2809, 2809. Hate that when that happens, but guys, I'm not there in class. There's nothing I can do. Okay, I can't start a whole video over. So, back up here. Just erase your notes, please. Back up here when I told you 53 squared was 2000. 2,089. That's really 2,809. Sorry about that. And now bring the 289 over and make it a negative 289, okay? And if you subtract that carefully, correctly, you're going to get 2520, 2,520. And yes, I'm sure about that. And then you're left over 34x here. Divide both sides by 34, and you're going to get approximately your x, your radius, is going to equal 74.1 feet. That's a really good problem. You understand all that you had to do was stand outside of a big water tower, know the distance from here to here, know the distance from here to where your line of sight is a point of tangency, and you can then find the radius of this big water tower without ever going on the inside and measuring it. That's pretty cool. Okay, all right, let's continue on. Let's take a look at our last theorem before we finish up with the inscribed and circumscribed circles. Okay, here's our theorem. Please copy this down. If two segments from the same point are tangent to a circle, then they are congruent. Okay, pretty cool. If two segments, if two segments from the same exterior point are tangent to a circle, then they are congruent. Copy that down and we'll talk about it in just a second. Please copy that down. If two segments from the same exterior point are tangent to a circle, then they are congruent. Students, go ahead and go ahead and draw a circle and draw two tangent lines, and we'll call these points A, B, and C. Okay, please quickly copy this down and let's talk about what this theorem is saying. Okay, first of all, notice your two tangent segments have to be coming from the same exterior point. They have to come from the same point, okay? So if AC and BC are tangent, and they have point C as a common endpoint, so let's look at this again. If AC and BC are tangent and they have point C as a common endpoint, then, now watch this carefully, segment, not line, segment AC is congruent to segment BC. Okay? Segment AC is congruent to segment BC. So let's look at this again. If I have a line tangent to a circle and another line tangent to the same circle, and they both come from the same exterior point, then this segment here will be congruent to this segment here. Now, I'm not going to make you do the proof, but the proof is really simple. It's not difficult at all, guys. Watch. Draw your radius. Draw your radius. What do you know? These two lines have to be what? Perpendicular. We just learned that earlier in Theorem 10.1. If a line is tangent to a circle, then it's perpendicular to the radius, okay? So, that has to be a right angle. This has to be a right angle here. Now, draw a segment here. And you have two triangles. Triangle ACD and triangle BCD. And we know they're right triangles. And we know the radius has to be congruent to a radius. And we know this side here has to be congruent to itself because the two triangles share this side. So guys, look what we have. We have a right triangle. Whenever you have a right triangle, all that you have to have is hypotenuse leg congruent from one triangle to another. triangles are congruent. So we'll call this triangle number 1, triangle number 2. I'm just trying to show you this real quick. You're not responsible for it, but look, triangle 1 and 2 are both right triangles. I have a leg congruent to a leg, and the hypotenuse congruent to the hypotenuse. So I know these two triangles are congruent. Thus, this segment here has to be congruent to this segment here, because if two triangles are congruent, then all of their parts are congruent. So it's really not that hard to prove it, okay? So if two lines are tangent to a circle and they come from the same exterior point, then this segment here will be congruent to this segment here. Okay, that's what Theorem 10.3 says. Now, let's finish up by looking at circumscribed and inscribed circles, and we'll be finished for the day, okay? I'm not going to give you definitions to memorize, but instead pictures of each one, okay? Now, this is called a circumscribed circle. Circumscribed, that means the circle is on the outside, and it's circumscribed around something, okay? So you know you have a circumscribed circle when the polygon that's on the inside has every single vertex lying on the circle. Look, if there is just one vertex that's not lying on the circle, then you do not have a circumscribed circle, okay? So copy this in your notes the best you can, okay? This is called a circumscribed circle. It's when a circle is surrounding a polygon, and notice every single vertex has to lie on the circle itself, okay? Very important that we see that. This is called a circumscribed circle. The circle's on the outside. Now, the next term is an inscribed circle, and think of the word in. That means the circle is on the inside. So it's going to be the opposite of this. Over here we had polygons being inside of circles. Now we're going to put circles inside of polygons, okay? And so there it is. This would be an inscribed circle, okay? Inscribed circle. And again, it's pretty obvious. Listen to me carefully, students. Every single side of the polygon has to be a tangent line. So is this side of the triangle tangent? Yes. Is this side of the triangle tangent? Yes. Is this side of the triangle tangent? Yes. Okay. So every single side of the polygon must be tangent to the circle. And when that happens, then you have an inscribed circle. Okay. Students, I hope this video has made sense. Please go back and watch the parts again that you need to watch to really understand the math well. If you have any questions, don't hesitate to call or email.